Welcome to Lecture 2.1, Rank and Nullity. The main goal of this section, not just this lecture, is to abstract the concept of a matrix as a linear mapping between vector spaces and study that. Advantages of this endeavor are that we get simple, transparent proofs that are not tied to matrices, and proofs that often adapt to infinite dimensional spaces where we don't have matrices. Now, not always. A lot of things don't carry over. But I'm intentionally holding off telling you what a matrix is as long as I can so we can understand the properties of linear maps first without matrices. Now, we all know that somehow matrices involve linear transformations. We saw that in introductory linear algebra courses. But it's not exactly clear how, and there's a lot of concepts that have been defined regarding or with a matrix, like rank and nullity is involving pivot rows and free variables and things like that, but they don't have to be. It's more clean to define them as a property of the linear map. And then there's other concepts like that of a transpose. So if you have a matrix like this, we all know that the transpose is what you get when you flip it about this main diagonal. You're basically swapping rows and columns. But what does a transpose really mean? Transpose is actually something that you get from any linear mapping between vector spaces. It's actually a mapping between it's an induced map between the corresponding dual spaces. So if we have a map from X to U, then there's a transpose map from X prime to, or U prime to X prime. And yes, when you do pick a basis and you get a matrix, the corresponding matrix of that transpose map is the transpose of the matrix. But that's coming later. I'll show you, not in this lecture, but in a couple lectures from now, what the transpose really is. And with a lot of these things, it's a lot more natural and clean to handle them in terms of linear maps than in terms of matrices. Let's remind ourselves the definition of a linear map, which is something we did in the very first lecture. So a linear map, sometimes called a mapping or transformation or operator, this last one especially if we are between spaces of functions, is a function between vector spaces, say X and U, both over the same field K. And I'm going to give names to properties that I gave earlier. So this first one, I'm going to say it means it's additive. You can break apart sums. And the second one, I'm going to say it's homogeneous. You can pull out constants. We'll call X the domain space and U the target space. Now, sometimes U is called the codomain, but I want to avoid that because I've been using the prefix co when speaking of the dual, things like covectors, and I don't want to overuse that prefix. Usually, we'll write Tx for T of X. So this additivity property is really just the distributive law. And this second property of being homogeneous is just saying that we can pull out, multiplication of constants and matrices commutes. It just means that T times AX equals A times TX if A is a scalar. And of course, that's true. So the notation is sort of suggestive of properties that we often take for granted, but are not going to be true for general functions. Next, I want to give you a number of examples of linear maps. I will go a little bit quickly because we've seen a lot of these before. So first, any isomorphism, I should say between vector spaces, is a linear map. Next, if X and U are spaces of polynomials of degree less than n, then the differential operator T is a linear map. And of course, I said less than n, but I could relax this restriction. I could say the infinite dimensional space of all single variable polynomials. Next, if X and U are R2 and T is some rotation about the origin, then that's a linear map. Now the origin is key here. If we have a rotation about some other point, that's not going to be linear. Fourth, if X is any vector space and U is the field that it is over, which is, remember, a one-dimensional vector space over itself, And then any linear scalar function L is going to be a linear map. Next, let x and u be the space of continuous real-valued functions on some interval, let's say 0, 1. Now I can actually weaken this to be piecewise continuous if I want. So let's let g be some fixed function in this space. Then the following is a linear function. So we integrate f of y times g of x minus y dy. So we're actually integrating out y, and we are left with a function of x. It's a little bit weird to think about, but this is called the convolution of f and g. And it comes up, especially in differential equations. You may have seen it if you've taken such a course. For example, if you want to model how much money you have in an investment that has a fixed interest rate, we all know that that is exponential growth. P prime equals r times p, so r might be like 0.05. But if you want to model the situation where you are continually adding or removing funds, then it's no longer going to be just an exponential function. It's going to end up involving the convolution. So I don't need to say too much more about that, but the convolution is, we say, a linear operator. Next up, something that should look familiar from your undergraduate linear algebra course. If x equals Rn, so things in here look like x1 up to xn, and u, so let's call this x, and then u is Rm. So let's think of things over here as vectors u1 to um. M might be smaller or bigger or the same as n. Then a linear map between these two is determined by specifying what each ui is in terms as a linear combination of the tj's. And so that's given by this. I'm specifically not going into too much detail on this because we will return to this when we study matrices. Because this is one of the things where notationally it's not clear why this is a matrix or how this represents a linear map if you haven't seen it before, but I assume most of you have seen this because you've taken an intro linear algebra course. So more on this later. So basically systems of, and this also represents a system of equations. So system of equations represent linear maps and so forth. So again, I'm going to shelve that till later. Our last two examples, like example 5, is something that comes up a lot in ODEs and PDEs courses. So this one, x and u are the spaces of piecewise continuous real-valued functions on the non-negative reals, and they have to be of exponential order, which loosely speaking means that they don't grow faster than exponential functions. Because if they do, this integral down here is not going to converge. So this is called the Laplace transform, and what it is you take a function f of t, and then you, sometimes it's called L, of time, and you spit out a function big F of s, which you can think of as frequency. So you multiply this by e to the negative st, and you add that, you integrate that up for the entire non-negative reals. And again, engineers like to say that this goes from the time domain to the frequency domain, and it's useful in ODEs because it turns derivatives over here, calculus, ooh, scary, into multiplication over here, much easier. Next, we have the Fourier transform. So this is typically defined for functions on the entire real line, and the reason why is because this f appears a function of time, and usually time starts, say time is non-negative, starts at 0 and goes on, and these functions down here are functions of space. So for example, like the temperature or the displacement of like an infinite rod, or just really long rod. So it's more natural to have an infinitely long thing rather than a half infinite long rod. So the Fourier transform is what you get when you integrate the function times e to the I c x over the whole real line. So both of these you can think of them as transforming from, so in this case, the spatial domain into the frequency domain. This is sometimes called f hat of c. And what you're doing is you are basically adding up the fundamental frequencies of the function over the entire real line. So for both of these things, actually, if you want to know more, I have a whole series of of courses on differential equations and then on PDEs and Fourier series. The latter is called Advanced Engineering Mathematics. And I have an entire lecture on the convolution up here in my ODEs course, and an entire section of lectures on Laplace transforms in my ODEs course. And then in my PDEs course, I have a lecture on, I think I have one lecture on Laplace transforms, and I have several lectures on Fourier transforms. One of them introducing it, and the other one applying it to solve PDEs. So if you want to know more about this, these are really fun topics. Even though I am not that type of applied mathematicians, I really like ODEs and PDEs. I think there's a beautiful mathematics behind the scene, especially in my PDEs course. I really emphasize how linear algebra comes up behind the scenes. So I don't go through linear algebra in the detail that I do in this course, but I do give an introduction to give the big picture, because linear algebra is so fundamental in so many areas of applied math and statistics and optimization. Okay, so moving on. Now we come to our first fundamental result. It says if T is a linear map from X to U, then first the image of a subspace of X is a subspace of the target space U, and similarly the preimage of a subspace of the target space U is a subspace of the domain X. I'll leave the proof of this as a homework exercise, but let me say a couple words because I didn't actually define what image and preimage are. So suppose that Y is a subspace of X, then the image of Y is what you think it is. It's just T of Y as a set. So that means it is the set of all T little y, where little y is in big Y. Or another way to say this is it is the set of all things in U, set of all U, such that U equals T y for some y in the subspace Y. Now you can use either of these to prove this, and I encourage you to try both to see which one is easier than the other one. You might learn something. It's good practice anyways. Next, the preimage. So now let me use a different color. Let me say that V is a subspace of U. So the preimage of V, sort of a picture of it. This is X, this is U, and here we have V. So that's gonna. So that is what is everything in U that maps to V. So let me use this notation, T minus 1 of V. So even though I said minus 1, I usually just say the preimage of V, so I don't actually say the minus 1. This is the set of all things in the target space, so the set of all X, such that Tx is in V. Or of course you could write this as the set of all things in the target space where Tx equals V for some V in V. Although that's not really much different. I think it's probably definitely easier in this case unambiguously to use this definition. Now sometimes I write this as PRE, say something like PRE sub T of V, just to emphasize the fact that it's a set. T inverse is not a map unless T happens to be 1-to-1. And even then it may not be defined on the entire space U. So I say this because I see common mistakes a lot, like T inverse of V. Here's an example of things that I see which do not make sense. So T inverse of V1 plus V2, people will write this as T inverse of V1 plus T inverse of V2. And this is bad. And why it's bad? So first of all, you can't do this unless it's actually a linear map. It looks like you should be able to do it, but if you think about what this is, like let me take an example that we've seen. So this is R3, and maybe you're mapping R3 to R1 by just the height. So it'll map this entire plane to this point. Then the preimage of, say this is 0, and this is, I don't know, 1, this is -1. So then the preimage t inverse of 1 is this plane here, and the t inverse and the plane, or the preimage t inverse of -1 is going to be this plane down here. So this is the set of all vectors that look like this, and this is the set of all vectors that look like this. Now you can, if you add these two subspaces, if this is y and this is z, then y plus z. Well, first of all, these are not two subspaces, but these are two sets. You can still add them like we added subspaces. This will generate all of R3. However, t inverse of 0, so if you take t inverse of 0, which is 1 plus -1, you're going to get this, the xy plane here. So moral is, even though something like this looks like it should be true, it does not make sense. Please don't do this. Okay, so now let me actually give some definitions that we will use throughout this class. The range of t, now this is a definition you probably know from like pre-calculus, is just the image of the entire space. So I'll denote that as r sub t, and the dimension of that is called the rank of t. The null space, often called the kernel in other areas of math, is just the preimage of 0. I'll denote that as n sub t, although a lot of times people write ker of t, or they might write ns of t. This is another common notation. There's a few others as well. So it's a set of all vectors that get mapped to 0. And the dimension of that space is called the nullity. The well-known rank-nullity theorem says that for any linear map T, its rank plus nullity add up to the dimension of the domain space. One way to think about this is if T, say, goes from R10 to R6, and let's say this is onto, so the image is all of this, then you're starting with 10 dimensions, and the rank in this case is 6-dimensional, and the nullity has to be 4 dimensions. So out of 10 dimensions, 6 of them persist, and 4 of them get collapsed. To prove this, notice that we have a theorem that's a lot like this. So if we have a subspace Y, let's say the null space, then we know that the dimension of that space plus the dimension of x mod that space adds up to the dimension of x. So all we have to do to prove this is to show that the rank has the same dimension, or sorry, not the rank, the range has the same dimension as x mod the null space. So we will come up with an explicit isomorphism between these two spaces. So let's let F be a map from, let's say, x mod nt to the range, x mod the null space to the range. Now we have to define what this is. So things in x mod the null space are equivalence classes. Let's say x bar. So remember that x bar is the set of all things of the form x plus z, where z is in the null space. I don't really want to call using z because I don't want to use n or k to represent a vector. So where does this thing get mapped to? Well, this thing, let's map it to something in the range. So let's say tx. Now, this is clearly onto. So this is because anything in the range has the form tx, and, well, this is what the preimage is. So this is clearly onto. We have to show it's well-defined because this definition depends on our choice of representative x. So if we take two things that are equivalent mod nt, let me write well-defined first. So let's say that x is equivalent to x prime mod nt. That's exactly what we mean when I say the
the equivalence class of x equals the equivalence class of x prime, remember? So then that means that by definition, x equals x prime plus z for some z in NT. Then f of x equals f of x prime plus z, which by definition, well, I should say f of x prime equals f of, sorry, x bar equals f of x prime plus z bar. I got to be careful what my domain is. My domain is a set of equivalence classes. So by definition, this is t of x prime plus z, which is t of x prime plus t of z, and that, of course, is 0. So t of x prime is, by definition, f of x prime bar. So that's why this is well defined. I've already said it's onto. I should probably just check that it's linear. I mean, I think this is very straightforward, but just to be safe, so no one calls me out on it. Let's take f of a x bar plus b y bar. This is f of a x plus b y bar, which by definition is t ax plus by, which is a tx plus b ty, which is a times f of x bar plus b of f of y bar. Okay, so it's linear. And finally, we want to show that it is one-to-one. So we've already said onto. So one-to-one. Remember what this means. If you always forget, it's easy to screw this up. So to this day, I still draw a picture of what one-to-one is, or better yet, what it's not. So that means that if you have some x bar and let's use y bar again. I don't like primes with bars. So x bar and y bar, that get mapped to the same element, which means tx equals ty, then it better be the same. Then it better be the case that these things were the same to begin with. So let's say that that f of x bar equals f of y bar, i.e. that tx equals ty. Then t of x minus y equals 0, which means that x minus y is in the null space of t, and that means that x bar equals y bar. Okay, so we are done. We have come up with an isomorphism between these two spaces, and therefore they have the same dimension. And by this previous result, which I don't remember what number it was, but it was from a previous lecture, the rank nullity theorem follows. Let's finish with several consequences of the rank nullity theorem. The first one is very simple, but it's also very useful, so it's worth saying. And what this says is that if we go from a bigger dimensional space to a smaller dimensional space, then the null space is going to be non-trivial. So in other words, there is some non-zero vector that gets mapped to 0. So here's a picture of this. This does not have to be onto, a little bit of a cartoon. So the proof of this, you can either just write down the rank nullity theorem and plug things in. Let me do that. So the rank nullity theorem says that the dimension of the range of T plus the dimension of the null space is equal to the dimension of X. And so this condition right here says, we know that the dimension of the range is strictly, is less than or equal to the dimension of U, and that's strictly less than the dimension of X. So what we have here is this thing, this thing here is strictly less than that. So what we can say is, that the dimension of the null space is equal to the dimension of X minus the dimension of the range, which is bigger than 0. because that is strictly bigger than that. So the dimension being non-zero means that there is some other non-zero vector in it. So thus, there exists a non-zero x in the null space. And that's what we had to show. For each of these corollaries, I will do an example. So this one revisits an example from earlier in this lecture where x is Rn. So you can think of this as the vectors have the form x1 up to xn, and they get mapped to things in Rm, which you think of as smaller vectors. So let's say u1 up to um. The corollary A implies that the corresponding system of m equations, so this is described by equals t11x1 plus t1n xn, and this thing here equals similarly t, to be careful that I say it right, m1x1 plus tmn xn. So this is, you've seen it in your undergraduate class, this can be described as u equals tx. I won't go into details of this. We will save it for later when we get to matrices. That this system of equations has a non-trivial solution. So there is some vector in here that gets mapped to 0, and such a vector corresponds to a solution to this system of equations. Of course, this is something that you know, you probably don't even think about it. If I give you a system of equations like this up here, say 2x plus 3y minus z plus 4w equals 0, and another one 3x minus y minus 3z plus w equals 0, you know that there's going to be at least one non-zero, non-trivial solution. Our second corollary is also simple. It says that if x and u have the same dimension and the null space is only the 0 vector, then the range has to be all of u. So once again, if we just write out the rank-nullity theorem, it says that the dimension of the rank plus the dimension of the null space equals the dimension of x. Now what this is saying is the dimension of the null space is 0. Then the dimension of the range has to be equal to the dimension of x, and by assumption this is equal to the dimension of u. So the range is a subspace of u of the same dimension, so they have to be the same. Well, actually, one thing I should add is this is assuming that these are finite dimensional, because we can certainly have a countably infinite subspace that embeds into another countably infinite subspace in a one-to-one fashion, but that's not onto. So let me actually add that condition that this is finite dimensional, and unless I say otherwise, I think in this class we can assume that things are finite dimensional, because when we get into infinite dimensional vector spaces, that is more in the range of real analysis and functional analysis. Let's also apply this to a system of equations. So something that you may remember from your undergraduate linear algebra course is that in any system, Ax equals b, the general solution is going to be of the form the homogeneous solution plus any particular solution. And in this particular case, homogeneous solution is just the null space of A, and xp is any solution you can find. And there's ways to do this. You set the free variables to be anything you want to, and solve the remaining system. So in general, this of course means that this is of the form z plus your particular solution, where say az equals 0. And there's a lot of different notations for this, so maybe you saw it in a different form. So if T is a linear map from Rn to Rn, that corresponds to an n by n system of equations. And let's assume that the only solution is the trivial solution. So geometrically, that means that we have Rn to Rn. Let me just draw a little cartoon of this. And by the rank-nullity theorem, the dimension of the range plus the dimension of the null space equals the dimension of x, which is the dimension of U, and of course the null space in this case is 0. So that means that the range and is going to be all of U. So this map is a bijection. So that means that 0 gets mapped to 0. Well, we know that's always the case, but there is a one-to-one pairing bijective correspondence between vectors in here and vectors in here. So if we want to solve an equation Tx equals U for some particular U, then this U is going to be some vector over here. And because this is a bijection, that means that there is going to be a unique X that gets mapped to it. So this has a unique solution. And that's something, of course, we know from this more general thing we learned, is that if the null space is trivial, then this is just the 0 vector, so we get a unique solution. But this is a more direct way to see it, because if the null space is trivial, then the range is everything, so this is bijective, and so any U you have over here has exactly one preimage over here. Okay, so that is the end of this lecture. We saw the rank-nullity theorem. We saw some consequences. And in the next lecture, we will see some applications of it. And when I say applications, I mean to things like polynomial interpolation and ODEs and PDEs. It's really cool, so stay with us.